Welcome to this talk about risk, fundamental ideas and concepts in risk assessment and risk management. My name is Tai Arben, and this is really in the core of my research, and it is a very exciting topic and is divided into 3 modules. First, I would like to address the concept of risk, some basic questions, then going into the concept, the metaphor of black swans, partly also addressing some issues of risk assessment, and then on module 3, more aspects linked to risk management. Okay, let's start with module 1. This is an offshore installation, an example of an activity we are producing oil and gas. Now, the question is, what is risk in this context? And I'm talking about risk related to certain accidents occurring, gas leakage, etc., etc. What is risk really saying? What is this concept? What's the meaning of this concept in this setting? Well, if you look into textbook, a lot of textbooks covering risk assessment, risk management, we often find this definition: risk is equal to expected loss. Probability times consequences, probability times damage or loss. It is just a terrible definition, I would say. It's really disappointing to see this definition being so often used. Not only in industry context, but also in societal context, we see this definition. It does not make sense. Risk is much more than expected value, probability times loss. Many aspects of risk uncertainties are not really captured by this definition, and it should not be seen as risk per se. It is just a metric of risk, yes, but it's not so informative in many cases. And let me give an argument for this statement. These are 2 distributions for the loss. One on the top is having a broad distribution. You can have quite extreme values of this damage X. In the lower case, you have quite a narrow distribution, so the losses are centered around this expected value. Now, these distributions have the same center of gravity. That means the same expected value. So they are the same. If you use this definition of risk, the risk management response should be the same. It doesn't make sense, because in the top case, you should of course be prepared for extreme outcomes. In the case with this X here, yes, you need to be prepared for that and have plans, preparedness measures for capturing these kind of events. But you don't care if your rule is based on expected value, only the center of gravity. These distributions are just the same. It doesn't make sense. So please do not use risk is expected value as the definition of risk. It is a metric, an index of risk, yes, can have some information in certain cases, but it's not risk per se. So there are other alternative ways of defining risk, and this one is often seen. Risk is events, scenarios, and consequences linked to them, and then also probabilities linked to the events and the consequences. We call this CEP or ACP, A the events, C the consequences, and P the probabilities. Or just the CEP, C the consequences, and P the probabilities. And typically we're using a risk matrix trying to describe this risk, where we have 2 dimensions, the probabilities and the consequences. This is really a common way of describing risk. It's much better than expected values, because you have both dimensions, consequences and probabilities. But it is not enough. I say, even this perspective is too narrow. We need to approach risk in a broader way. Let me give an example trying to motivate this. You are walking on the street. A person comes up to you. Let's call him John. He has a die and he offers you a game. One game only. You're allowed to throw this die. You're allowed to throw this die. And if the result of this die is 1, 2, 3, 4, 5, you get $6,000 from him. But if, on the other hand, the result is 6, you have to pay him $24,000. I ask you then, what is the risk seen from your perspective? So, the die is showing 1, 2, 3, 4, 5. You get $6,000 from him. If, on the other hand, the result is 6, you have to pay him, John, $24,000. What is your risk? Yes, the answer would be, if you have sort of this idea of risk being consequences and probabilities, is 6 and minus 24, probability 5, 6 and 1, 6. Is this risk? Yes, it's a description of risk, you can say, but it's really, really poor. This is not risk, a good description of risk. It is just terrible, because I'm saying the most important aspects of risk is not captured by this understanding of risk. The key aspect of risk is not here. So we can present this kind of risk description, but it would be rather not very informative, not informative at all, because the key aspect of risk is not covered, namely that the risk linked to if this die is fair or not. We have assumed, tacitly, just presumed that the die is fair. But how can we do that? That's the key point, really, in this case. John is probably cheating. I mean, on the long run, he will sort of lose money if he's not cheating using this die, if that was fair. So the issue whether this die is fair or not is really the important aspect of risk, and we have tacitly just said this, that is the case. And this is what we do often in risk analysis. We have to make assumptions, a lot of assumptions, to make these calculations work. These are examples from an offshore oil and gas quantitative risk analysis, and we make a lot of assumptions. We assume, for example, there will be no hot work on the platform, etc., etc. Have you heard about any major accidents occurring where all procedures are followed? Never. So these assumptions can conceal a lot of important aspects of risk. We need to reflect these also in some way. Now we typically put all these assumptions in an appendix, and they're not really a part of the risk description. In some cases they are, but very often I see they are more or less included as a part of the risk description. They are essential and they need to be addressed. The risk linked to them need to be addressed. So these are some of the main sort of challenges by using this kind of probability-based approach, which I now have sort of discussed. First of all, assumptions can conceal, as we saw in this example, important aspects of risk and uncertainties. And that's also linked to point number 4, surprises occur relative to these assumptions, like in our case. Assumptions are really critical and surprises occur relative to our knowledge and beliefs, given partly by these assumptions. Number 3, the probabilities are always conditional on certain knowledge. And you can have a risk matrix. You have 2 cases. In one case, you have very strong knowledge, and one case, very poor knowledge about the phenomena that you are studying. But you get the same probability number. So, the probabilities are not really reflecting the strength of the knowledge that these numbers are based on. And this knowledge and the strength is obviously of great importance for the strength of the risk assessments being performed. And number 2, these kind of probability analysis are often using, let's say, some sort of probability models, frequentist probabilities, which are sort of creating these probability models. And these are really presuming the existing of stable processes. The phenomena are not sort of changing, they are stable. So what you're doing actually is to exclude the possibility of surprises even from the start by simply assuming this probability model would apply. The stability will rule. But you cannot exclude the possibilities of some surprising things occurring relative to this stability. Okay, so what we are doing is to suggest and recommend that we extend the current thinking about risk being probability-based, historical data-based, and add aspects of knowledge, uncertainties, and surprises. How we do that, I will come back to. But this is really the basic idea. What I try to highlight here is the need for extending the current thinking from probability, historical data, to in some way capture the knowledge and certain dimensions and surprise dimensions. That is the challenge. So, and this is the way we recommend considering risk. You have an activity, think about the oil and gas installation, and from this activity you can have some events occurring like a leakage, gas leakage, a blowout, ship's collision, leading to some serious consequences like loss of life and damage for the installation. We don't know what the consequences will be when we look into the future. There are uncertainties. And this combination is really risk. You have the activity, it can lead to some consequences, and you don't know what these will be when you look into the future. And some of these are undesirable losses and damage. This is what the concept of risk is really all about. And let me give an example. Yes, we have this pipeline with a lot of hydrocarbons, and there is a possibility to get a leakage, a rupture of this pipeline, giving a leakage with some consequences for loss of lives and for material damage, environmental sort of damage, economic loss, etc. If you look at this now, in the future, you don't know if these events and these consequences will actually happen, occur. There are uncertainties. We are facing risk. So risk is the consequences of the activities C and uncertainties we don't know what C will be. This is risk. This is the concept of risk. Then the question is, how big is this risk? How large is it? Then we must use some way of describing these uncertainties. And probability is a tool we have for describing how confident we are about these events to occur or not. And these probabilities also have to reflect knowledge aspects. And I mean, they are at least conditional on the knowledge. So we need to reflect also knowledge into this risk description, and also take into account that we can get some surprises compared to our knowledge. We also need to reflect that in some way. In a more formal way, we can then say that we can describe risk by this triplet, the consequences that we have specified, see marked. Let's say we look at the number of fatalities. That's one way of sort of pointing to C marked. It could be some economic loss we would like to look at. And then we need to have a measure of uncertainties. And I just call it Q here. It could be probability. But probability is not a perfect tool. So we need maybe also to include other aspects to capture the uncertainty dimension. Qualitative statements could in addition be used. And then we need to address the knowledge, K here, that these judgments are based on. And it's of course relevant, is this knowledge strong or weak? So then we have this distinction between the concept of risk, CU, and how we describe, characterize risk. We are facing risk, we're looking at this installation, obviously, but how large it is much more difficult to say something about. And it's certainly not objective. It's based on the data we have, observations we have, but we also need to make judgments. These are subjective to some extent, or at least intersubjective among certain analysts, experts. It's not objective, this risk description. But we are facing risk, certainly. But how large that risk, that's not so straightforward to determine. So what we're doing is to take the traditional perspective on risk based on probabilities, historical data, risk matrices, etc., and extend this by incorporating the knowledge, uncertainty, surprise dimensions. We're not throwing away everything we have. We are extending the current thinking. And in this way, it's much more easy to deal with knowledge building, transfer of experience and learning, which are so important areas in applications, but it's so difficult to incorporate in the risk thinking. Yes, if you have a traditional perspective and think about a risk matrix, and you get more and more information, more knowledge, but the probabilities are the same. Your risk is the same. It doesn't make sense. In this new perspective, knowledge is captured in the risk description. So what we get of knowledge building is changing the risk description because it's a part of the risk description in a different way than we have in the traditional perspective. So this is just an example of how we can easily extend sort of a risk matrix type of analysis by giving a color to the events if they are supported by a strong background knowledge or a weak or poor background knowledge or something between. So here is the red is poor and the green is the strong background knowledge. That is informative. In this case, we also have shown some interval, some, let's say, 90% prediction interval for the consequences. We are 90% sure that the consequences will be in this interval. Also important to reflect. This is the same thing using the risk matrix in standard form in just 3 categories or 4 categories for the probabilities and the consequences. 2 events that are green, where you have strong background knowledge, and 1 red, where you have poor. So this is just saying that the informing us by just having the probabilities is not sufficient, because the probabilities of an event A is conditional on the K, the knowledge, the background knowledge. And the strength of this one we need to include as well. So then we need some sort of system or structures for reflecting when we have strong or poor knowledge. And this can be done in many ways, but this is just indications of some of the aspects that we could use to decide whether it should be strong or poor. We can look into some judgments about the assumptions being reasonable, realistic, the data information exists and are reliable and relevant. Is there disagreement among the experts? Do we understand the phenomena we are studying? Do we have accurate models, etc., etc.? I don't go into this further into details, but I think we can see how we can use this to classify in some way what is strong and what is poor. So going back to this extension of the risk perspective, we are going to leave the probability historical data perspective, add knowledge, add surprise dimensions. But we will come back to the third one on surprises in the next module.